Right, let's get started. Welcome to day -1 of the bootcamp. I hope Josh didn't make that joke already. So, my impression, I may be wrong, is that many people who come to the bootcamp are looking to learn to use Python to do data analysis. And so, not everyone, thank you. And so a lot of what we've been doing so far gives us some groundwork for thinking about how to do data analysis in Python, and this lecture is about the SciPy module, the SciPy package, which provides a great many libraries to enable data analysis effectively with Python language. So even if you aren't interested in analysing data, I think there's plenty in here to keep you interested. So, Brad spoke about NumPy on the first day, and so you're familiar with import NumPy. SciPy, similarly, can be imported with that command. Sometimes you might import SciPy as SP, for instance, like you import NumPy as MP for convenience. Also, I think many of you know now about launching the notebook with PyLab, which loads NumPy and SciPy by default, and also with inline plots. This is the framework I'll be using in this presentation, but you don't have to follow it. Okay, so SciPy, this is the main website for SciPy, scipy.org, so you can open that in your browser and have a look. SciPy is the scientific toolbox for Python. It's aimed at mathematics, science, and engineering applications. It's built on top of NumPy. It's included in the input Python distribution. And the reason it's built on top of NumPy is that NumPy arrays are the most practical data type to use in this sort of data analysis. They're generic, they're efficient, and they're straightforward to handle within Python. SciPy is open source software and it's compiled on top of NumPy. SciPy is also a conference that's held each year that focuses on scientific Python discussion. There was a recent meeting a few weeks ago. Website you can look at is there, and you can see Josh's plenary address from there, which is talking about science with Python, so that's interesting to look at. And also the talk and tutorial by Fernando Perez. All very worthwhile to look at. So here are some resources. I guess my idea here is that after this lecture, if there's something particular that you want to know further about NumPy, you can of course ask us, about SciPy rather, you can of course ask us. But you can also use these very excellent resources for getting to grips with different aspects of the SciPy package. So there are some lectures provided by GitHub, so they're constantly being updated. There's also some older lecture notes from Travis Oliphant, who founded NCORE. And then there's a few others. And I also want to draw attention to this in particular. I don't know how many people are coming to Python from a MATLAB background. While we don't proselytize too much, we think there's a very strong case to be made for leaving MATLAB behind and doing all of your analysis in Python. And so I'll be spending a little bit of time in this lecture talking about how to make that as easy as possible for you if you are coming from a MATLAB background. And this cheat sheet, which is basically like a one-to-one correspondence between MATLAB command and SciPy NumPy command, it makes that transition extremely straightforward. Even if you aren't coming from MATLAB per se, you might have some knowledge of other statistical environments like R. We think R is fantastic, but Python provides a lot of power as well. So these sorts of one-to-one correspondence maps between languages make it very easy to map between languages. So, SciPy is structured as a large package with many sub-modules, and each of these sub-modules contains many functions and routines that provide particular scientific functionality. Here is a list. It's not exhaustive, though it contains it describes most of the development functionality in SciPy. In this lecture, I'm going to talk about SciPy generally and symbolic computation, and then I'm also going to talk a little bit about specific packages. Linear algebra, Fourier transforms, optimization, integration, and interpolation, which, in my view, are all fundamental scientific tasks that we would want to accomplish with Python. So, that's the structure of what I'll be talking about for the next hour. Okay, so I'm going to start with an overview of SciPy and of symbolic computation in Python. Are there any questions before I move on? Any questions so far? Hopefully everyone can import SciPy. There's one over there. Yes?
One question for your first name, you had PyLab equal sign.
Yeah, I should have said, that's with the most recent version of the notebook. You don't need the equal sign there, but you can certainly put it in, I think. So one of the most fundamental data analysis tasks is getting data in and out of a language. So you might have your data in a flat file, might be an ASCII file with text, columns. Maybe it's in a SQL database. That's something we won't be talking about, but Python does make it very easy to get data out of that format and put it into Python for manipulation. And so Josh gave a little overview of I/O. Actually, it wasn't little, it was quite substantial. And then there's also like a cookbook on the SciPy website which studies specifically using SciPy to get data in and out, okay? So Python and NumPy provide very generic, very powerful, but quite low-level read and write routines for ASCII files and some binary types. So 9 times out of 10, that's maybe what you're going to want to be using. There are also like, these are examples of some of the load and save formats which you might have encountered already. There are also provided within the scipy.io module a number of routines for loading proprietary or common binary formats, for instance from IDL or from MATLAB. I should ask, when I say MATLAB, I hope some people have at least heard of MATLAB and know what I'm talking about. And similarly with IDL, so maybe some of you would understand why you would want to be doing something like this. Okay? So this is what the scipy.io module provides. Provides support for a number of proprietary data formats, MATLAB, IDL, HDF5, which is not strictly proprietary, but that's provided by the PyTables module, which is very powerful. It includes support for very advanced data structures in these languages. And so here's an example using MATLAB data. You import the IO package, then you're going to load from something that's saved as a MATLAB file into a Python data structure, and then that's it. That loads the structure. And then similarly, if you want to save something from Python, I don't know why you would want to do that, but if you did, then you would use the save map command. Okay. Okay, so I'm going to go through now a bit of discussion about manipulating data once it's in Python, or generating, constructing, and manipulating arrays within Python. After this little section of keynote slides, I'm going to go over to the notebook and go through examples of all of these in the notebook. So yeah, I'll move fairly quickly through this and then we'll talk further while we're going through the notebook, okay? So when you load the PyLab environment, or when you load NumPy, when you import NumPy as MP, you gain access to a number of functions which allow you to build short arrays very quickly. For instance, linspace creates linearly spaced numbers between A and B, n of them, so that's a useful function that I use very frequently. This row concatenation, this is not strictly a function. As you can see, it's got square brackets rather than parentheses. It's a hack that allows you to concatenate things very easily. It's very useful, but it's also not especially elegant, as you can tell from that R underscore. So you should try that out and see how it works. If you want to construct an n-dimensional grid of coordinates, which is something I'm frequently doing, the mgrid command within NumPy allows you to do that, and we'll go through an example and see what this means in a moment. And similarly, if you're looking to concatenate and tile arrays, column-wise or row-wise, there are these functions that allow you to do that. Okay, so maybe I'll switch over to the notebook now and we'll go over that those first few topics, and then we'll talk further about symbolic mathematics. So let's go. Hopefully everyone can load a view of the notebook or even the raw notebook itself in either version 2 or version 3. Okay, so while we're going through the notebook, this is a great time to ask questions if something isn't clear, and I'll try to answer it, or more likely someone from the audience will be able to tell me the answer. Okay, so here we import NumPy and SciPy. You guys are masters of this sort of thing now. So NumPy and SciPy generally provide quite different functionality. NumPy is like the basic array structure, very powerful, quite low level. SciPy is more high level, like scientific analysis routines, interpolation, integration, but there is a bit of overlap between the two, to the point that there are even methods that apparently do the same thing that are in one and also in the other. They're not quite identical though. This is my favorite example of this. The NumPy square root function, for instance, if you throw a negative number into it, gets upset and returns nan. Maybe that's the appropriate thing to do. SciPy, on the other hand, understands what you mean. And so in this case, I've taken e to the pi I plus 1, which is 0, and so it's returning something that is 0 to within machine precision. So there are differences between these functions. In general, my rule of thumb is that SciPy is more geared toward like mathematical thinking. So if you're like taking the square root of -1, it will know what you mean by that. Whereas NumPy is really like machine computer data structure, and so square root of -1 doesn't make sense in that context. Okay. There are many examples of this. This is just one, so please do look on the SciPy website to see, learn more about the differences between these two. Okay, so let's go through now an example of getting data in and out of SciPy. I'm going to import some MATLAB data. So we import the I/O module, so import SciPy I/O as SIO. Everyone now is understanding what that's doing? Yes?
Question, if the SciPy function is more general in the scope of variables it can handle, does it make it slower? If we take the unit square roots with the two different functions in NumPy and SciPy, is the NumPy faster then?
My impression is that I wouldn't expect it necessarily to be faster, no. The best way to answer that question would be to look at the code, which is one of the great things about Python. You can you can try to look at some of the code that's compiled to make these functions, and then you'll be able to answer that question. I would resist your characterization of the SciPy square root as more general. It performs more generally in this case, but I wouldn't say it's more general overall. And performance-wise, I don't think it would make a difference. Both are heavily optimized. Okay, so we import, oh yes, sorry.
So the previous example commands that you loaded,
yeah.
I would run it on the IPython through the terminal. Do I need to do mp.exp and mp.py for everything, because you keep saying that it cannot identify those functions even after you
mp dot square root you're talking about?
the other ones, exp and py.
Oh, okay. So what's happened here? Yeah, thank you. I'm mixing my namespaces here, which is bad, so it's very good that you've drawn attention to it. I've loaded this notebook with the pylab command. So if you're in the terminal, you could run %pylab, and what that does is makes available to you all of the pseudo MATLAB functionality within IPython. So that automatically, for instance, puts NumPy and SciPy into your namespace, and those functions become available to you. So what's happened here is that exp and pi are in my base namespace because I've loaded this notebook with pylab. Then on top of that, I've also imported NumPy as MP, which this is an example of something that's terrible to do, so it's great that you brought it up. And then mp.square root is that being referenced that way. I could not include that MP, I could just make it square root, and it would still work in this environment because square root is also made available by the pylab namespace import.
So I used to IPython and then pylab, pylab.
For instance, alternatively, you could put np.exp and np.py if you imported NumPy as np. And in fact, I would recommend doing that if you were writing like code that was going to be run. But if you're just in the interactive environment, then pylab is a good way to do it. Thanks. That was a great question. Anything else? Great. So we import that module. There we go. And so I've made available a test file. I hope I have made available this test file. If not, it's on. Those of you who stuck around late into the GitHub lectures will know how to get all of this information. It's on our.
It's on the website.
Oh, it is on the website? Okay, good. So you can download this into the same directory where you're running a notebook or where you're launching IPython. And so this allows you, this is an example of importing this data structure from within MATLAB. So that's it, it's one line. And then if I introspect, I look at the structure, you see it has a lot of information, like very generic information, and then the actual like data itself. Here it is. And if I just want to pull out the data, note that this is stored as a Python dictionary. So if I want to pull out the data itself, which in this case is called box, that's the variable, and I just do that, and the data is loaded. So for those of you who are playing along at home, an exercise at this point might be, what are the dimensions? How would you find the dimensions of the imported array?
What is a struct?
Struct is just a variable here. I just decided to call it struct because it's representing a data structure that I have imported, but you could call it anything. Any other questions about that? Okay. So let's go over some of the examples of vector and array manipulation that I mentioned in the slides. So constructing sequences, either linearly spaced or logarithmically spaced sequences, is something that one will commonly do in data analysis. So here's an example of using the linspace command. This constructs endpoints starting at A and ending at B. So I'm going to construct 57 points that start at 50 and end just below 100. There you go. Very useful. Similarly, if I want to use logarithmically spaced points, this is 20 points between 0.1 and 10. So it's base 10 logarithm. There you go. And often one will want to construct coordinate arrays. And so mgrid provides an example of this. Note again these the square brackets rather than parentheses. That's hack territory when you see that, but it's okay. So what this does is creates, well, I'll demonstrate. It creates an array, a two-dimensional array, and this works in n dimensions, but I'm just using 2 dimensions here, of x coordinates and then an array of y coordinates. And so you can think of these as xy pairs on a grid. Okay, and so it's the array represents the grid, and the value of x and y at each location is the x coordinate and the y location, the y coordinate at that location. And the reason this is useful is that very often one would want to construct in an array some function, some data that extends radially. So here's an example of this. So here at the origin, this represents like a grid where at the origin it has the value 0, and then as you get further out from 0, it has value equal to the radius from the origin. And then this is an example of constructing a tile array by tiling together x, which is, again, a linearly spaced array, with x squared. So you can see what's happened there. X, which is this array, has been concatenated with x squared in a column-wise fashion. That's what C underscore does. Similarly, one can use row underscore, R underscore to do row concatenation. Okay, so that's an overview of questions, it's an overview of some of the basic SciPy functionality. So it's a good point to ask questions here. Thanks.
Sorry, you comment on why it's square bracket and
Not in detail. It's to do with, Fernando answered this at the last bootcamp, and so I've unfortunately forgotten the answer. But it's to do with the way these aren't functions in the usual sense. They're some workaround. Do you remember? No. It's some hack. Yeah.
It's good that you noticed that that's weird.
Will it actually be a function?
No, there's other ways to do concatenation that,
right,
that are more Pythonic.
Right. I think the reason this was put into NumPy is that they wanted functionality that resembled other languages people were familiar with when they were coming from Python. So this sort of enabled that, but as you can tell, it's not very Python. Yeah.
It's a way of using the hooks that looks up an attribute by value. And
exactly. Yeah. It's somehow like it's magic, really. Yeah. It's entirely unclear to me how that works.
Another question.
Yeah.
In the notebook, you have log space. That's like lin space, but it's logarithmically spaced.
That's right. Yeah. I often use that because I need logarithmically spaced coordinates in some of the analysis that I'm doing. Yeah.
Could you repeat what you said about using underscore to make it columns, and how do you make it rows?
Yeah, so the question was, can I just go over a little more detail about using this underscore concatenation and an example of how I will do that with rows. So let's have a look at what this does. So as you can see, this is from a module within NumPy called index tricks. And that's your first indication that something strange is going on here. And so what it does is it translates a slice object. And so when you take square brackets through a NumPy array, that's getting a slice from the array. And this is translating that slice object into concatenation. It's transmuting it as metal into gold. So, to answer the question that was asked.
How did you add the cell just below that?
Sorry?
How did you add the cell just below?
Control MB. If you do Control MH, you get a key list of keyboard shortcuts. That's your best friend. Okay, let me try this and see what happens. What do you think is going to happen when I do this? There are two possibilities in my view. One is that I will get row concatenated, so that'll be like this and this, or there'll be an error because the dimensions of the arrays are not lined up correctly. No, it was a third possibility. It stacked them row-wise along one row. Does that make sense? So that concatenated along a row, and that concatenates along a column. I don't know if that really answered your question, but at least you can see how to do it in your own notebook, how to use the R_stands.
Yeah.
Good. Okay. Are there more questions? Yeah.
So when you put in the question mark, there's this little window that comes in from below, right? How do you make it go away?
So let's have an example of this. So if I call up the help like this, I make it go away by clicking here. Do you see this? There, gone. I hope that works for you.
Graham, do you want to just mention that there are other, I mean, maybe this is shorthand for doing these techniques,
Sure.
but there is actually ways to do this.
So mp.tile is a way of like repeating arrays, and there's also hstack and vstack. So that's stack. This is a regular function, so that stacks arrays. So maybe I'll even try that. Let's see what happens. There you go. So I got an. Oh, what do I have to do? I have to give a list.
Yeah.
Okay. So that achieves the same thing as row concatenation. And let's have a look at vstack. Okay.
Why not use those?
Go right ahead.
No, it's the same thing? Or
Yeah.
Do people prefer one or the other? Or is there advantages to using one or the other?
No, I don't think. I don't think there's. It's.
You want to transpose the result.
Okay. Yeah, that will work. There we go. There's.
So performance-wise, I think they're mapped to each other. I only use hstack and vstack because it is more common. And varying
In
from MATLAB.
In principle, R_ would allow you to take a slice. No, I don't think there's any difference. No, I don't think Okay. We'll talk a little bit about symbolic computation in Python now. Symbolic computation is manipulation of algebraic symbols. Some of you might be familiar with Mathematica or Maple. So this is not strictly concerned with numerical manipulation as it is with symbolic manipulation. So there's a Python package called SymPy, Symbolic Python. This is its homepage that allows you to do a lot of very good symbolic computation in Python. It's still being developed. It's not Mathematica for Python quite yet, but that's its aspiration, and it's already quite a long way along that route. Homepage, documentation, and yes, think of SymPy as Mathematica for Python. You can import SymPy this way. They recommend using from SymPy import star. This, you should be exercise caution when using any command like this because it will clobber anything in your namespace that has the same name as the function that it's importing. But we're going to do that here. Do most of you have SymPy installed already or not? Like if you run import SymPy, do you get an error or not? It's okay? Okay. All right, well, let's go through this quickly then. So, if I add a half and a third, what do I get? I get 0. That's right. Because it's doing integer division. 1 on 2 is 0, and 1 on 3 is 0, and then it's adding them together. So, this is still Pythonic integer division, but if we want to define these as fractions, that is as rational numbers, 1 on 2 and 1 on 3, SymPy provides data structure, data type to do that. So that allows us to add fractions. And note that this, because they're rational, it does this to perfect precision, it does it exactly. If I want like a float representation of that, I use the eval_f function. So in this case, I'm evaluating 5/6 to 6 decimal places. There it is. And of course, if I wanted this without importing SymPy, I could do 1 dot on 2 dots. So this casts these numbers as floats, and so it does float division, and then I get something quite similar. Okay. So this is just using Python, and this is using the rational data type with SymPy. SymPy provides functionality for doing calculus, doing many things with symbolic variables. So the way this is achieved is by declaring the variable you want to be manipulating as a symbol. So now x is a pronumeral, it's a variable. And in this function takes the limit of sin x on x as x goes to 0, which is 1. It provides differentiation. So this is the error function, differentiated with respect to x, which is a Gaussian, a normal distribution, a bell curve. And similarly, it provides integration. So if I want to integrate a Gaussian, I get an error function. And so that's an example of indefinite integration. And I can also specify ranges. In this case, can anyone guess what the minus OO means? It represents infinity. So OO is a special variable that's imported in SymPy that represents infinity. And so this integrates this function from minus infinity to 0, and then provides, and then evaluates it to 3 decimal places. So if I run this, I should get, there we go. Okay, so those are some of the basic operations in calculus, but within SymPy you can look for the other things that are provided.
If you don't want the dot or float operator, you can import division from future.
Yes, thank you. So in Python 3, integer division has been deprecated, I suppose, and so it's now just float division. And so in general, when you want to import some future functionality, in this case, you can use from, is it like this?
Yeah.
Import division, okay? And so now we've gone into the future and brought division back to us. And so now if I do 1 divided by 2, I get a half. Okay? So in the future, this is what the world will be like. All right. Thank you. So SymPy also provides matrix manipulation and computation, and this is like not arrays, numerical arrays, which NumPy provides, but actual symbolic manipulation of matrices. So here's a basic matrix. It's represented pretty clunkily, but you can see it's 2 by 2, 1 x, x, 1. X, remember, is a symbol we've declared still. One of the fantastic things about the notebook is that it allows you to load some rendering tools like SymPy printing. So here we go. And this prints these matrices in a much nicer fashion. So here I'm going to take the inverse of M, and then I'm going to be now rendering it with the fancy SymPy rendering. There it is. So you will have seen briefly pop up like a long latex text string, and that's what was returned by SymPy when it performed the inversion, and then the SymPy printing in the notebook rendered this as that lovely array. And similarly here we can do like a Cholesky decomposition of that matrix, and we get a similar thing.
Question?
Yeah.
Before you loaded SymPy printing, in the previous statement you've got pprint, pretty print, and what does that do?
So if I just print M, in fact I think now that I've loaded the printing, I think it will, okay, now here we go, this is good. So if I just print M, this is what I get. Can you see what it is? So it's still clearly a 2 by 2 matrix, but it's kind of 1, x, x, 1. So pprint stands for pretty print, and this is a SymPy thing, and it just prints things that look a little nicer. So let's have a look. So this will just print an expression in a nicer looking form. In this case, it doesn't make a tremendous difference, but in cases where you want to, for instance, render an integral in the terminal, it can use some more versatile Unicode features to make it look a little nicer. Yeah. Yeah.
How do you pull the tech that describes the matrix, the tech code?
That's a good question. There is a way to do this, and I have forgotten. Does anyone know? So the question was, how do we pull the tech code for the matrix that's been rendered?
Yeah.
Fernando would know, but I don't. Oh, here we go. Show map as tech commands. There we go. And so then you can copy that. Thank you.
There is a way to have it directly print out into a string that. I'll figure it out.
Oh wow, there's all these things in here. Anyway, you can play around with that at your own pace. Sorry?
Can you do that latent thing on terminals too? I mean, through your code, can you make that from the latent commands?
No. The terminal is not capable of rendering this, but you can use pretty print, which is about the prettiest you can aspire to. Sorry, go on.
No, I just want to know if I can get the latent code out from the.
Oh, I see. Yeah, there must be a way. We'll get back to you on that very shortly. Okay. Where's my presentation? Okay.
You have the empty brackets earlier, and then they disappeared.
That's I need a bit more information.
When you p-printed the first time, you had 3 rows of brackets. You had 1 x, and you had empty brackets. Then x1.
I don't follow. When I don't remember.
P-print and you did that earlier.
Like this?
Yeah.
So pretty print is a function. It accepts an expression, in this case m.
Yeah, you had that empty set of brackets
like that?
on your output. Empty row, right? Empty row.
Your matrix.
This.
Yeah.
So pretty print attempts to render the matrix in a way that is visually obvious. And so this is representing a 2x2 array. And it's trying to indicate to you that this is like the columns and this is the row dimension. This is pretty print inserting an extra line to make it look square, because it's a square matrix. Does that make sense? If you think it's pointless, then that's fine. Just printing M is still pretty clear in this case. But if you had a 10 by 10 matrix, maybe this format wouldn't be so useful. I don't know. Yeah? Like this? So I think what will happen now, you can see because I've loaded this module, it's being rendered now. Because I've loaded this module, everything subsequently will now be rendered using this SymPy printing. So things will look nice, but they aren't that way by default. If I unloaded that, or if I restarted the kernel, then it would look not as nice as that. I don't know how to unload an extension module. I would interrupt or restart the kernel, unless that was a huge pain. Okay, let's move on. SciPy provides some functionality for interfacing with other languages. So if you have some background in high-performance languages, C, C++, Fortran, you might very much want to use the high-performance capability of those languages within Python, using Python as a glue language or a framework language to do sort of data manipulation, and then the numerically intensive part of your code could be outsourced to a language that's better suited to nested for loops, for instance. So there are many ways to do this within Python. And an interesting list of possibilities is at this website. So it compares, for a quite sophisticated example, how you would do it in different ways within Python. The most comprehensive option is Python, and that requires a lecture all of its own, which I believe we will not be doing, but I think in AY 250, for those who are going forward with their Python, there will be more of that. What I will be talking about very briefly now is F2Py and SciPy Weave. There is also a just-in-time compiler called PyPy. You have a Python script, a .py file, you run PyPy, that Python script, and it compiles very quickly, and it doesn't create binaries or anything like that. It essentially compiles that code and then runs it. And so it's almost like magic. It will speed up your Python code quite a bit, but it's not fully versatile in its support. For instance, it doesn't support NumPy or SciPy, so it's not terribly useful. Sorry?
It's kind of good working.
Yes, that's right. Or I feel sometimes I opine on these different things. You know, this person does this module does this. These are all fantastic things, and they're all like public contributions, so we laud all of them, right? But it's important to know what things do and don't do. Thank you. Okay, so let's talk quickly about F2Py and SciPy Weave. F2Py is a little separate to SciPy. It's an interface with, sorry, here's the question.
What are your little arrows? IREF, Psycho, where are those?
So it means that Cyclone was inherited from a previous package called Pyrex, and PyPy came from something that was called Psycho. Yeah, so you might find mentions of these on the web, and now you know that they're sort of... And this isn't really necessarily a one-directional arrow. Like, this has gone into many different packages, and I'm simplifying a lot of important history. Okay. So let's see. So for using these interfaces between languages, you will need a compiler for the high-performance language that you're compiling. For instance, for F2Py, you'll need a Fortran compiler, G95 or G-Fortran, and of course, you'll need the F2Py command. So some of you may find that you have F2Py installed already. If you're in the terminal and you type F2Py, it may be there. And many of you may have installed GCC, or you might have other Fortran compilers like G-Fortran on your computer. If you don't worry, you can follow along. Similarly, using Weave, which we'll do an example of in a moment, requires a C compiler. So I think most of you will have had GCC on your computer or will have installed it during the setup process. So let's try this out in the notebook to give an example. So what I've done is provide a very short snippet of Fortran code. This is not a terribly good example of what you would use this interfacing for, but at least it shows you how it works. This is a piece of Fortran code. It's Fortran 90, so for those of you who are expecting 6 spaces at the start of each line, you should get with the program. Fortran is a wonderful language. So what this subroutine does is take in 2 variables, A and B, and returns 2 others, which are the sum and the product, C and D. So hopefully it's clear what this subroutine is doing, even though it's probably not clear why you would want to do this in Fortran if it wasn't for an example. Okay, so important things to know are that you declare it as a subroutine, you specify all the variables, both the in and the out, and in the declarations, and it's important, you have to declare, you have to specify which are the incoming and which are the outgoing. Anyway, so you can download this example, so you should have this code, and then once you have that, you can compile it using F2Py. So F2Py runs on the command line, which is why I've got this exclamation mark. Exclamation mark in the notebook runs something on the command line. F2Py, and these are the compiler flags. I'm compiling the G-Fortran, and I'm compiling this Fortran snippet into a Python module called example. So I do this, and you get a whole bunch of text, and it looks like it doesn't work. I mean, unknown vendor G-Fortran, what's going on? Oh my goodness, this looks horrible. And then you get to the end, and it doesn't. You don't even know what's going on, but it's worked. And if you look in your directory, you will see there's now a file called example.so. This is a compiled library. Don't try to look at it in your terminal. So this is a module that can be imported into Python. So if I now import example, it's been imported. And if I look at example question mark, let's see what happens. So it tells me it's a module, and it tells me where it is, and it's even got a little doc string. It tells me it's been auto-generated, and it provides a little example of how I would call the function within that. So I'm going to run example, which is the module, example.arithmetic, because arithmetic is the function. So here are 2 variables, A and B, and now I run example.arithmetic on them. And it returns 2 values, the sum and the product. Note that because it returns 2 values, it returns them as a tuple. Yeah. Similarly, if I wanted to set those into variables, I could use C, D equals. So I do that, and then C is 92, D is 1092. Okay.
Type LaTeX parentheses, capital N.
LaTeX, capital N? Oh, there we go. I should have been able to guess that, really. So to answer the question that was asked earlier by how do we get that in the terminal or in any way, the LaTeX function will render an expression in TeX.
And that's important because he did from SIMP import star. It's inside of SIMP.
Oh, really?
Yeah.
Okay. So there's no TeX. That's probably a good thing. Okay. Sorry. Thanks, Josh. Were there any questions about that or about F2Py?
So let's say if I were doing a loop and I put the loop in a Fortran code and I follow it through Python, is the non-function really happening in Fortran, the compilation part of it, or how's the work being divided now?
That's exactly what's happening. And so that's a great example of what you would want to use this sort of thing for. Python is slow at processing nested loops. The reason for that is interesting, but the bottom line is very often in scientific computing you will want to be doing something inside 3 or 4 nested for loops, and high-performance languages like Fortran are very good for that, and so you might write a subroutine that processes that. When you run F2Py, it compiles that subroutine and then provides a wrapper that allows Python to be able to call that subroutine and run it natively. And this shouldn't shock you, because whenever we're calling like a NumPy or SciPy routine that's all high performance, that's all that's going on. There's some compiled low-level code that's heavily optimized, and there's a wrapper to it in Python. And that's what NumPy and SciPy are essentially providing. They provide many things, of course, but this idea of compiling a separate language and then having an interface to Python is something that's very generic across the language. It's one of the great powers of Python, how easy this is to do. Does that answer your question?
So in the last line there, you were returning 2 values from a function. Is that something you can do with Python?
Absolutely. Okay. So this is if you want to unwrap a tuple that's being returned, or a list that's being maybe just a tuple that's being returned from the right-hand side, you use C, comma, D, comma, however many there are.
Technically, you're only returning one object, but he's returning a tuple, and he's immediately assigning the values of that tuple to C and D in turn, the elements of that one object. So you could return back, an instance of a cookie jar if you wanted to, but that assignment of C, comma, D to one instance would really make sense. It makes sense because that's a tuple. If you return back a list, it would also make sense. Right. If you want to assign it in that way.
So note if I put A, comma, B, it automatically understands that it's processing as a tuple. And I don't know if this is possible. Yeah, so you can swap the values of variables this way. AB equals BA. Does that make sense? I'm setting A to have the value of B and B. There were more questions, I believe. Did I miss anyone with a hand up? Yes?
I just wanted to demonstrate you had a Fortran program, how you just call it in line with Python. You said it's very easy. Is something you want to show us? Can you show us?
Sorry, this is what I was attempting to do here. Was it not clear why that was happening? So there was a snippet of Fortran code, which I showed. There it is. This next step compiles that code and provides a module that I can import that calls that code. That makes sense?
Perfect.
Then I import that module, which is called example, and this provides a function from that which accepts 2 arguments and returns 2 functions. Does that make sense? And so that's an example of calling a function. Is that your question?
Perfect.
Okay. Any further questions? Okay, let's look at an example with Weave. I think
that's going to fail for some people that don't have a compiler.
Yeah,
it's not critical that you get this part.
Right. So this is an example courtesy of Nat Butler. What I'm doing here is creating 1,000 points between 0 and 1. As with Python, there are many ways to do this. A range is one way of doing it. And I'm creating a storage space. I'm creating an empty array Y, and we're going to be processing something going from X to Y. So the idea of Weave is that it allows you to write code from another language, in this case C, as a string. In this case, you can see it's a 3-quote string, and I've just literally written this code here. And then Weave allows you to compile that code inline and apply it and pass it variables that you've defined within Python. So I do that. Oh, what happened there?
You didn't execute this. So.
Oh, I didn't execute the cell bar. Thank you, Josh. So there we go. So this command compiled this snippet of code, passed it these variables, and ran it. So that's pretty nice. And if I look at y now, I can see that this function is defining, remember we made x go from 0 to 1. This function is defining y to have some value in 0 to a half, and then a different value going from, we'll see what it looks like in a moment. Is there a question?
So, textually mapping the variable names to the variable?
That's right, yeah. There's more sophisticated functionality than that, but this is the basic example, yeah.
Do you, as you write your C or your Fortran code, do you need to do it in a way that's particularly Python conscious or formatted in a certain way?
No, the idea would be that you're writing code that enables you to pass in Python variables in this fashion, but then within your string, you're doing C. Any further questions? Yeah.
How do you know that whatever types of variable types you have defined in Python will work in Python recognize dictionary or the C recognize dictionary or anything like that?
So if you were doing using more complicated data structures, then you would have to either try to coerce them to work within C, within Weave, or you would use Cyclone, which is another C to Python mapping, which allows this more sort of sophisticated things. Or you would do all of your data structure manipulation within Python and then just try to pare down the high-performance language code to the minimum that you need. That's what I do, and it's what I recommend to others, but there might be circumstances where that's not possible. I wanted to show just, like, this is what we were doing here. So x goes from 0 to 1, and we're defining y to have different values over different ranges. So that's a relatively simple example, but it shows how you can do that. Gives an example of compiling code. Yes?
In the code itself, before y and before x, you have an asterisk.
Yeah.
What's the function of that?
So this is not Python code, this is C code. This is telling C that these are pointers. And so I'm not going to talk about what pointers are or about C ever again. There was another question over here.
I was just going to make one note of what zeros means and ones and empty, and maybe make the distinction for that, and perhaps even do a time it on empty versus zeros.
Okay. Let me make a meta comment. So Josh was asking me to talk a little more about these functions that I've just mentioned in passing. We're assuming now that you guys, we can just throw functions up on the screen, and you guys know how to work out what that is. So in the notebook, for instance, np.zeros question mark gives you the information about this function, how to call it, and what it does. And so there are a number of different functions, like ones, which define empty arrays or arrays populated with one or very basic data types. And so Josh was recommending I do a time it on...
Do make an empty array, empty, 100,000 or something, and do the same thing with zero. Because you had said explicitly, I'm creating an array that's going to be where I'm going to stick the results. And you're talking about high performance. Okay, now try that with ones or zeros actually.
Yeah, and I'll talk about the difference between zeros and empty in a moment. Okay, so does anyone want to have a guess or suggest what the difference between empty and zeros is, and why one is faster than the other by a factor of 10?
What does empty have?
Nothing. So it assigns a chunk of space, but it doesn't populate with anything. Whereas zeros is populating with zeros. Yeah. For that reason, one can be much more efficient than the other. This is almost like malloc in C. So allocating. I said I would talk about C.
You don't know what values are in empty. It can be random values.
Exactly. They're going to be, because nothing's been assigned there. It's just random blocks of memory. It's whatever was there previously. We don't even want to look at that probably.
It will render if you
Yeah.
create an array.
Absolutely. So let's do this. Oh my goodness. Look at this raw memory. Beautiful. Yes. There you go. Amazing. It's like the Matrix. Okay. Any further questions? So this is okay. I anticipated that this might happen. So we've gone through the first chunk of the lecture notes, and this has been an introduction to SciPy and symbolic computing and blending languages between Fortran, C, and Python. Okay, so this only scratches the surface of SciPy. I mentioned at the beginning all the different packages that can be used within that SciPy provides, and so we don't have time to go into all of those in detail. In fact, at this point we have no time to go into any of them in detail, but I will. For the breakout exercise, and also more generally, I've provided a set of 3 data analysis challenges that use SciPy and hopefully teach you to use SciPy packages and functionality to do basic data analysis tasks like integration, interpolation, Fourier transforms. If that's of no interest to you, that's okay. But if you're familiar with these types of tools and have been wondering and wanting to learn how to do that in Python, my hope is that the notebooks, which are linked on the website, will enable you to do that. The breakout exercise is going to be one of these, the third one, so I'll just talk about what that breakout exercise is quickly. There are three notebooks, like I said. Each one of these is doing a different kind of data analysis challenge. We're going to focus on this third one, which is fitting a model to data. Let's not worry about whether it's covariant or not, unless you would like to. And so this is going to use scipy.optimize and scipy.linalg, which is the linear algebra and the optimization modules. Okay? And so I'll talk a little bit now, because there's a little bit of stats background, and I'll talk about that quickly now, and then the breakout exercise. So I'm very much throwing you in the middle of things here. I've said that there are these modules and that they do optimization, but I've not told you anything about how they work. And so you will be doing something like scipy.optimize.tab within the notebook or within IPython, and that will give you a list of all the functions available. Or you might be looking on the website, the SciPy docs, and of course the notebooks themselves have many hints, so I'll be talking about those. Okay. So whenever I'm trying to do a new data analysis task in Python that I don't know how to do, this is generally what I will do. I will look at the doc page to understand how SciPy provides the functionality that I want to carry out, and then I will start tabbing in IPython to understand which functions are available, which ones I'll use. So let's just focus on this third task, fitting a model to data. I'm recommending this because it strikes me as a fairly generic task that might be useful for everyone to know how to do in Python. So let's skip ahead. So we're going to be using the linear algebra and optimization toolboxes. You might import them in this fashion, or however you like. I've provided a data set in the form of sp3data.txt, I believe it's called. Is that linked on the website? Not yet, sorry. It is in the GitHub repository, so it can be linked easily. And it provides a data set in the form of x, y, and error bars. So it provides a set of x, y coordinates like this, and some error bars on the y coordinates. And the task that we're going to carry out is to fit a model to those data. And I've picked a model that's smooth, but also quite non-trivial. This is the functional form of the model. And I wanted to do this to indicate the versatility of this model. So very often, we will only want to do something as simple as fitting a straight line to some data. You could also, you could do that this way. Other languages and environments might provide sort of one-shot routines that fit a straight line to data. I encourage you to be thinking about fitting things to data in this fashion, because it provides very versatile and powerful techniques for doing sort of any sort of fitting to any sort of data that you encounter. So if you can master this sort of technique, you're in a very strong position with regard to data analysis. Okay? And the way that we do it is we have a model. Okay, and in this case, all we're going to be fitting is the overall amplitude of that model, one parameter p. And we define a goodness of fit function So when I say define a function, I mean what we will be doing is within Python, we will be defining these as functions. And then we will use this SciPy routine. It's in scipy.optimize, which optimizes the goodness of fit function with respect to the parameter that we wish to fit. And it will provide, it will tell you which parameter value best fits this data. So that's the fundamental task of data fitting. Let's have an example. So here we go. So if you import fmin from scipy.optimize, so this is in the scientific programming, this is the lecture notebook. There's a bit of information here about what optimization is and what the fmin function does. And so I'm going to give an example here, which is kind of similar. Here's a function, x, y, and I would like to optimize it. I would like to find its extreme values. And I've chosen this function carefully for a reason. It's to demonstrate the difference between local and global minimum. This function has a little minimum around here. And then clearly it also has things tailing off down here. If I optimize starting at this value up here, my SciPy optimizer wanders around and it finds the minimum and it reports it here. Ta-da! And so it says 1 is the location of the minimum. That's on the x coordinate. There it is. And its value, current function value, is -1. Does that look right? Yes, it does. So hopefully, I scrolled through this quite quickly, but hopefully if you define x and y as functions in this way, note, very important, what fmin accepts is a function. So I've defined y as a lambda function, which takes in a generic x value and maps it to the value x cubed minus x squared minus x. And when I'm plotting, I plot linspace, a linear vector of x values, y of x. There we go. So if I start the optimizer up here, it wanders into the local minimum. And if I start at a different location, for example, over here, it wanders down here and gets upset because, of course, it can't find the minimum because this just goes down to -infinity. This is an important point about optimization. This isn't a problem with Python. It's doing the right thing. But when you're dealing with functions that don't have global minima, you will get this sort of behavior. And more to the point, if they have many local minima, you will find different minima depending on where you start. So the fmin function accepts the function you wish to optimize and the starting value of the parameter you wish to optimize. And where you end up depends on where you start. That's a generic feature of optimization routines. Nevertheless, the Python implementation of these routines is very powerful and enables you to do optimization and parameter fitting very easily, very powerfully, very quickly. So what we'll be doing in the breakout is fitting a function to data in this sort of fashion by optimizing the parameter value that goes into a goodness of fit function. So I'll launch that notebook in a minute. And in fact, I'll take questions now and then I'll launch that notebook and we can get into the breakout exercise. I'm sure if there are questions about the breakout exercise, please do ask them now. Questions generally about SciPy or anything? No? We'll get straight into the breakout exercise then. So hopefully most of you can load this notebook. Put your hand up afterwards if you cannot. Sorry, I want the third one. Sorry. So there are 3 notebooks. We want number 3. This is fitting a curve to data. And so I've provided quite a bit of information to this already. And so your goal should be to edit this code, add in the extra functionality you need to fit the curve to the data that I've provided. And you can use this as a template if you like, or you can do your own thing. Do whatever you like. But the goal obviously should be to use the SciPy optimized functions. This notebook does more than just fitting this curve to data. It also fits it, assuming covariance between the data points. So if you can get all the way through this notebook, I would say you've essentially mastered a large chunk of data analysis. But that's not, it's not all for the breakout session. Okay, so let's do the breakout now, and please ask questions along the way. Yeah, I should have said that's with the most recent version of the notebook. You don't need the equal sign there, but you can certainly put it in, I think. Okay, Okay, so one of the most fundamental data analysis tasks is getting data in and out of a language. So you might have your data in a flat file, might be an ASCII file with text, columns. Maybe it's in a SQL database. That's something we won't be talking about, but Python does make it very easy to get data out of that format and put it into Python for manipulation. And so Josh gave a little overview of I/O. Actually, it wasn't little, it was quite substantial. And then there's also like a cookbook on the SciPy website which studies specifically using SciPy to get data in and out, okay? So Python and NumPy provide very generic, very powerful, but quite low-level read and write routines for ASCII files and some binary types. So 9 times out of 10, that's maybe what you're going to want to be using. My idea here is that after this lecture, if there's something particular that you want to know further about NumPy, you can of course ask us, about SciPy rather, you can of course ask us, but you can also use these very excellent resources for getting to grips with different aspects of the SciPy package. So there are some lectures provided by GitHub, so they're constantly being updated. There's also some older lecture notes from Travis Oliphant, who founded NGOR. And then there's a few others. And I also want to draw attention to this in particular. I don't know how many people are coming to Python from a MATLAB background. While we don't proselytize too much, we think there's a very strong case to be made for leaving MATLAB behind and doing all of your analysis in Python. And so I'll be spending a little bit of time in this lecture talking about how to make that as easy as possible for you if you are coming from a MATLAB background. And this cheat sheet, which is basically like a one-to-one correspondence between MATLAB command and SciPy NumPy command, it makes that transition extremely straightforward. Even if you aren't coming from MATLAB per se, you might have some knowledge of other statistical environments like R. We think R is fantastic, but Python provides a lot of power as well. So, all right, let's get started. Welcome to day -1 of the bootcamp. I hope Josh didn't make that joke already. So, my impression, I may be wrong, is that many people who come to the bootcamp are looking to learn to use Python to do data analysis. And so, not everyone, thank you. And so a lot of what we've been doing so far gives us some groundwork for thinking about how to do data analysis in Python. And this lecture is about the SciPy module, the SciPy package, which provides a great many libraries to enable data analysis effectively with the Python language. So even if you aren't interested in analysing data, I think you'll find there's plenty in here to keep you interested. So, Brad spoke about NumPy on the first day, and so you're familiar with import NumPy. SciPy, similarly, can be imported with that command. Sometimes you might import SciPy as SP, for instance, like you import NumPy as MP for convenience. Also, I think many of you know now about launching the notebook with PyLab, which loads NumPy and SciPy by default, and also with inline plots. This is the framework I'll be using in this presentation, but you don't have to follow it. Okay, so SciPy, this is the main website for SciPy, scipy.org, so you can open that in your browser and have a look. SciPy is the scientific toolbox for Python. It's aimed at mathematics, science, and engineering applications. It's built on top of NumPy. It's included in the import Python distribution. And the reason it's built on top of NumPy is that NumPy arrays are the most practical data type to use in this sort of data analysis. They're generic, they're efficient, and they're straightforward to handle within Python. SciPy is open source software and is compiled on top of NumPy. SciPy is also a conference that's held each year that focuses on scientific Python discussion. There was a recent meeting a few weeks ago. Website you can look at is there, and you can see Josh's plenary address from there, which is talking about science with Python, so that's interesting to look at, and also the talk and tutorial by Fernando Perez, all very worthwhile to look at. So here are some resources. I guess these sorts of one-to-one correspondence maps between languages make it very easy to map between languages. So, SciPy is structured as a large package with many sub-modules, and each of these sub-modules contains many functions and routines that provide particular scientific functionality. Here is a list. It's not exhaustive, though it contains it describes most of the development functionality in SciPy. In this lecture, I'm going to talk about SciPy generally and symbolic computation, and then I'm also going to talk a little bit about specific packages, linear algebra, Fourier transforms, optimization, integration, and interpolation, which, in my view, are all fundamental scientific tasks that we would want to accomplish with Python. So that's the structure of what I'll be talking about for the next hour. Okay, so I'm going to start with an overview of SciPy and of symbolic computation in Python. Are there any questions before I move on? Any questions so far? Hopefully everyone can import SciPy. There's one over there. Yes?